Right. Hi all, welcome back. In today's video, we want to talk about the partial derivative. Now, we spent a lot of time talking about limits. We spent a lot of time talking about vector functions, parameterization, vectors, 2D space, all that stuff, 3D space. But now we actually want to start talking about the actual calculus that we'll be doing. And that starts with the partial derivative. This is one of the most fundamental ideas in math. It's the generalization of the derivative that takes the derivative beyond 2 dimensions, or beyond 1 dimension, and off to 3 dimensions, and 4 dimensions, and 5, and so on. So it's a generalization of the derivative. So we're going to be spending a ton of time talking about it. This is going to be one of our longest units, along with the next unit and the unit after that. We've got 3 long units coming up. But anyways, the partial derivative is the multivariable analog to the normal derivative, or to the single variable derivative. And so what it does is it allows us to take derivatives of cross-sections of multivariable functions, which is very important, and we can use it to find tangent planes to multivariable functions, but that will be discussed much later. So let's start talking about the partial derivative. So we can define the partial derivative in a very similar way to the normal derivative, but we call it the partial derivative because we take derivatives by parts. We do not take derivatives of multivariable functions as a whole. So if I wanted to take the derivative of a two variable function, I'd get 2 derivatives because I'd take one derivative with respect to x and one derivative with respect to y. That's why we call it partial, because we're taking it with respect to one variable. So I can define f sub x, which is the partial derivative with respect to x of f of x comma y, is equal to the limit as h approaches 0 of f of x plus h comma y minus f of x y over h. So we're only perturbing this x value. So if I have a graph, I'm only going to be perturbing one value and the other value is going to remain constant, okay? And then we can define very similarly for the y derivative. So the partial derivative with respect to y of f of x y is equal to the limit as h approaches 0 of f of x comma y plus h minus f of x comma y over h. So that is how we define the partial derivative, but now we want to talk about notation. So I can use this notation, which works fine, but I find that notation personally to be a little bit clunky. So we've got plenty of other notations that we can choose from. One of which is just f sub x, which is a pretty simple one. Or maybe you've seen this in physics if you've taken physics E&M yet. But partial f by partial y, or by partial x, this curly d symbol is the partial symbol, so we write a partial derivative the formal way, which is this notation. Then we get partial f by partial x is equal to partial x sub, or partial sub x of f. So I can put the partial symbol here, I can put the variable I'm differentiating with respect to there, and then I can put the function there. That makes sense. And we can also, of course, write it in more expanded notation. So if I want to take the partial derivative with respect to x of f of xy, I can just write that. And then, of course, we can do the same for y. F sub y of xy is equal to f sub y is equal to partial f partial y is equal to partial sub y f, right? That all makes sense. Now, why don't we try discussing how we can take these derivatives? So essentially, if I'm taking a derivative with respect to some variable, then I'm going to take a normal derivative, but I'm going to treat every variable that isn't being differentiated, I'm going to treat it as a constant. So if I take a derivative of a function of x and y with respect to x, then if I see a term with y in it, I'm going to treat the y as a constant. So y squared will be a constant. Y cubed will be a constant. Anything with y in it will be a constant. Okay, so I think that makes sense. Now why don't we try an example? So I'd like to differentiate with respect to each variable the following function, f of xy equals x cubed plus y squared, x cubed plus x squared y cubed minus 2y squared. So if I want to differentiate with respect to x, I differentiate this term just normally. It's just monomial differentiation. Now this term, this I treat constant, so that just stays y cubed through the differentiation. This I differentiate, so that becomes 2x, so I get plus 2x y cubed. Now this is also just a constant. What's the derivative of a constant? Well, it's just 0, so I get partial f by partial x is equal to 3x squared plus 2xy cubed. Now if I want to differentiate with respect to y, this will be 0, this will be constant, and this will become 3x squared, so I get, or 3y squared, so I get 3x squared y squared, and then I differentiate this, and then I get 4y. Okay, so that's really how you differentiate, and all of the differentiation rules apply. We will be discussing a more nuanced multivariable chain rule, but that will come later. But differentiating these could all be functions. You could use the single variable chain rule if you're only dealing with a composite function of x, or a composite function of y if you're one variable. It's very simple. And of course, there are higher order derivatives and partial derivatives in 3 dimensions, 4 dimensions, 5 dimensions. It's very expandable. We're just covering the 2-dimensional case because it's easier. Now we can kind of see what we did here. So if I take this function, which is the function that we're dealing with, what I said earlier was that taking a partial derivative is like taking a derivative of a cross-section. So let's say I wanted to find the partial derivative of x. Let's say I wanted to find f sub x at 1, 2 or something. And I'm not exactly sure which axis is which here, but let's say this is the x-axis, and I'm drawing some I'm drawing some x equals 1 here. And then I want to find the derivative at y equals 2. So y equals 2, let's say, is right here. So the point 1, 2, 0 is right there. And now what I'm going to do is I'm going to look at our graph. So let's say our graph, if I take the cross-section at this picture right here, so if I intersect here, and I go up, and then I go down, then I go up, then what I'm looking for is I'm looking for the cross-section. I'm looking for the derivative at the cross-section. So what I'm getting is a tangent line, something like there. So what I'm finding is that I'm finding the tangent line at the ordered set right there with respect to x. So with respect to x means I'm taking it like that. If it was respect to y, I would be taking it along this axis, and that would yield a different value. But anyways, again, it's fairly simple. In the next video, we will look into taking partial derivatives of more functions, applying them to situations, and looking at implicit partial derivatives. All right, thanks for watching, and we'll see you in the next time. Bye.